Okay, this is Dr. Smith. Let's dive into this review sheet, shall we? So, to start with, problem one, of course, is Star Wars, as always. Han Solo trying to escape the planet Hoth, and the Millennium Falcon. He has to get to a point where little g for Hoth is 0.100 meters per second squared. So, what's happening is, here's the planet, and Han Solo has to get out to a point where that's the value of little g. So the planet has a mass of the same as Earth, and its radius is the same as Earth as well. So R equals RE. Okay, so let's see. Basically, the way you do this is you take, to find the field, you take a test mass, and you say the test mass times the strength of the gravitational field is equal to the gravitational force on the test mass. So there's your mass of the planet, there's big G, and little mass, and then R squared. So R here is the distance he has to be from the center of the planet. Then that brings the gravitational force of the Millennium Falcon down to this here, which is equal to its mass times little g. So, let's see, so we can do this. We can say little g equals, we can just cancel the little m's, of course, big G, big M over R squared. And what you can say, one thing you may remember here is that if you plug in the mass of Earth and you plug in the radius of Earth as your distance from the center of the planet, you should get the Earth's surface gravity, okay? So, let's see, GE, which is the, well, I can't draw an E to save my life today. Call that an E. Okay, that's G sub E, which I'm going to say is Earth's surface gravity, is going to be capital G times mass of the Earth over radius of the Earth squared. Okay, so that is Earth surface gravity. Okay, so the trick I'm going to use here is I like to pretend that little g on the Earth's surface is equal to 10 meters per second squared. It's not quite, but it's pretty close. So what I'm going to say here, in fact, is that the surface gravity on Earth is approximately 10 meters per second squared, and in fact, that is 100 times what we need little g to be at the point where the Millennium Falcon can go into hyperspace, right? Which is right out here. So we're looking for a point which has, let's see, right, so what I'm going to say is g at our hyperspace point, so I'll call that g sub h, gh over surface gravity of Earth is equal to 1 over 100, okay? And if we plug in this formula here, so actually I probably should have written this the other way, gh over ge equals, and then we can plug in this formula here, this guy here for gh, and this guy here for GE, and what you'll get is let's see, so this is going to be big G mass of Hoth, which is the same as mass of the Earth, and that's going to be divided by your R squared, okay, and that's going to be over G times mass of the Earth again, divided by RE squared. And so what happens then, time for a color change, yeah, I like red, is that of course your G's and your ME's cancel. And so what you're going to get is this is 1 over r squared, or 1 over little r squared on top, and 1 over big RE squared on the bottom. So that's going to be equal to RE squared over r squared. So what you'll get, then we want to find what r is, right? So I'm going to take this, and remember this was equal to 1 over 100, and do the old cross multiplication. And down here, I'll get r squared equals 100 RE squared, or R, this is your hyperspace point, where you can safely go to hyperspace, is 10 times RE. Or 10 times the mass. What the hell? I don't want that. Okay. So there we go. And that is the answer. I mean, you can plug in RE if you want. And of course, you can go back to, say, this point and plug in the mass of Earth here and then find what little r has to be to give you a g of 0.1 meters per second squared. But I like to do it this way because I don't have to use a calculator, and, it's neat. Okay, so in part B, we had to find the work done by the Millennium Falcon's engines to get it from the surface of Hoth to the hyperspace point. So let me see. Oh, right. That's how I got another one. Okay, so let's draw Hoth in, well, I'll draw it in white, except that will never show up. So let's go back to black. Okay, so here is the planet Hoth, and the Millennium Falcon starts on the surface. Okay, so I'm going to say this is point 1 here. And then out here is where hyperspace is. Okay, so initially we're going to say kinetic energy is, well, so let me just back up to how we always do these work problems. Total work done on the Millennium Falcon is the change in its kinetic energy. So we say it doesn't need to have any particular kinetic energy when it gets to the hyperspace point. So we'll say that's 0. It starts on the surface with a kinetic energy of 0. So then we can also say, that's easy. Sorry, I'm all over the place here. So the things doing work on the Millennium Falcon are gravity and the engines. So work done by gravity and work done by the engines equals delta K, which is 0. There's no change in kinetic energy. Okay, so work done by, work done by the engines equals negative of the work done by gravity, and work done by gravity is going to be the negative of the change in gravitational potential energy. Gravity is a conservative force, which means that the work gravity does is the negative of its change in potential energy. So that's going to be negative, negative, so positive change in gravitational potential energy. Okay, so the work done by the engines is going to be the final gravitational potential energy, UG at point 2, minus the initial gravitational potential energy, UG at point 1. That's supposed to be a 1. Okay, so let's see, what's our position here? Well, here our position is r equals little re at the beginning, because Hoth has the same radius as Earth, right? So that's how far we are from the center of Hoth. And out here, it's going to be little r equals our answer from before, which is 10 re. Again, you might be slightly different depending on what you did, but it's fundamentally the same thing. And so the formula for gravitational potential energy, you will recall, is capital G times mass of one thing times mass of the other. In this case, the planet Hoth and the Millennium Falcon. And over the distance between their centers, and crap, there we go. That is, of course, negative. Okay, so remember, gravitational potential energy is 0 when the two objects are very far apart, and then gets smaller as the distance between them decreases. Okay, so, well, when I say gets smaller, I mean it's getting more negative. So, coming back over here, work done by the engines is, so we take the potential energy at point 2, which is negative big G, big M, little m, over, and our radius, or our distance between the two at point 2 is 10 re, and then it's going to be minus negative, so I'm going to go ahead and do, just to make it clear what I'm doing here, stop it. Okay, this here is UG at point 2, and then UG at point 1 is big G, M, and this is the mass, big M is the mass of the planet, which is the same as mass of Earth, so pretend there's a little ME in there. There we go. And over RE, la 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 la, and let's see, where can I make space for this? So this is going to equal big G, ME, little m, over RE. Yeah, I've just ran out of space. So this is going to basically be 1 minus 1 over 10. Okay, so this thing here times this thing down here, which is 9/10. And what you should get from this, let me grab ye old TI-89 that some student a long time ago left in my room. And, oh, come on, stupid piece of crap. Yeah, I guess that's it. Okay, so let's see, 6.67 E negative 11 times mass of the Earth, which is 5.97 E24, times mass of the Millennium Falcon, which is 400 metric tons, which is 400,000 kilograms. And then we divide that by the radius of the Earth, which is what did I say? 6371100, and then that all gets multiplied by 9/10. Gives the work, which is 2.25. Yeah, okay. So work done by the engines is going to be 2.25 times 10 to the 13th joules. And in case you're wondering, that is a hell of a lot of energy. I mean, to get a spacecraft, with our technology, to get a spacecraft from the surface of Earth out to 10 Earth radii takes these massive boosters. And when you launch a spacecraft to do that, the vast majority of the mass of it is fuel. So the Millennium Falcon, the fact that it, just chug along and they don't have massive, huge fuel tanks they have to drop off as they go, means obviously they've got some really freaking advanced technology. And of course, laser swords and stuff like that. Okay, anyway, that's the end of problem 1.